Now there is another thing, electron capture as well. Now for the electron capture, you have a scenario in which any X nuclei having proton number Z and atomic mass number A, if you have a certain scenario in which there is a nucleus having positive charge here, Z unit of A, and there are electrons revolving around this. So when I talk about heavy nucleuses, then in the heavy nucleuses, these radii are actually more closer to the nucleus. Okay. Then the radii of these electron orbits is more closer towards this. So there is a high probability that electron gets captured by this nucleus because of the electrostatic interaction between the electron and this nuclei positive charge, huge positive charge. If electron gets absorbed by this nucleus, then what will happen? Now there should be charge balance as well in the process. Then if one proton and one electron, the charge with respect to one proton per positive unit of E and minus unit of E, there should be zero charge, obviously. And that means there is only one possibility, that proton gets an electron and the compound state gets converted to neutron. Okay, so similarly this is happening here, a proton absorbing electron or a nucleus absorbing electron, and there is a proton number reduced by one factor, 1 unit. Okay, so this is the state with respect to an neutrino. We will account that factor later. Okay, so for the energetics of this, you need to apply the same process, that the Q electron capture, the value of this value should be positive for this reaction to happen. Now you can put this value, that the reactant mass is, the total reactant mass is this, the mass of nucleus plus mass of an electron, and mass of the product mass is only this mass of this. Okay, so when you convert this, actually, now there is another factor, binding energy of the electron. Okay, because there will be energy emission. So if you convert this to the process, that the mass, this mass m a z minus z m e, now again m e minus m n a z minus 1 into c square. Okay, so this z m e plus m e is z minus 1 m e, and when you convert this mass of nucleus to the mass of atom, then there will be z minus 1 unit of me as well, and minus sign will bring out the subtraction of these two terms. Okay, so the remaining thing is this ma z minus ma z minus 1 into c square minus b. So for electron capture to occur, the QE should be greater than 0. That implies mass of this nucleus or atom should be greater than, atomic mass should be greater than these two values. Okay, so for the electron capture. So these are the three things, 3 beta decay processes. Okay, so the next thing is that how do you notice, or how do you find out that there is a beta negative decay or beta positive decay or an electron capture process? So for obviously for beta negative decay, now for beta negative decay, you need to put a chamber in which the radioactive substance is here, as is the substance. And if the substance, now if I apply the magnetic field in this chamber, now this is a evacuated chamber, means there is complete vacuum inside the chamber, and if I apply the magnetic field, obviously magnetic field can propagate because EM wave propagates through the vacuum. Then if you apply the magnetic field B, uniform magnetic field, and this is emitting beta particles, beta negative, beta positive. Okay, and electron capture is also happening, in which electron is getting captured by the nucleus, and there is no emission of any beta particle. Okay, electron and positron. Now there are two kind of particles are coming out from the. Now if the beta positive decay is happening, then you know the process, you know what will be the interaction of beta positive particle. Beta positive particle mean elect positron with the magnetic field. Now this particle will certainly have some velocity, because this is getting emitted out by the nucleus, and there will be some kinetic energy of the beta particle. Because of that kinetic energy, it will move, and if it moves, then you can say that inside the magnetic field it will experience some force, and that force is a magnetic force which is q v cross b. Okay, if you apply b in such a orientation that b is perpendicular to the initial velocity, the particle will follow a certain trajectory, and particle will go in a circular arrangement, because the when particle experiences magnetic force, it follows a trajectory, a circular trajectory. Okay, so if particle is going in this circular arrangement, means there is this kind of interaction, and because of this, the q, now q is obviously positive, e positive, v cross b is equal to mv square by r. In circular arrangement, the v cross b is perpendicular, that's why we have circular fashion. That implies that evb is equal to mv square by r. Okay, my writing is not so good here, so just adjust this. Now obviously, if the positive charge is happening, if we have an electron, if we have a beta negative arrangement, beta negative decay, then the magnetic force will be in the opposite direction to this. The magnetic force will be into minus ve into v cross b, or is equal to minus evb. Now the direction of the particle is completely opposite to the direction of this particle. So you can identify that what kind of beta decay we are having, a beta positive decay or a beta negative decay. So you can identify. Now this is also known as beta spectrometer. Okay, and this is beta spectrometer. According to your books, now this book is modern ABC. No, sorry, modern. So this is beta particle spectrometer. Okay, there is a radioactive source here. This is your radioactive source, and it is just we used a lead block here, and if we apply the magnetic field here, then particle will follow some circular trajectories. Okay, so the particle will undergo some this kind of force, and you can measure the velocity of the particle. What is the velocity of the particle you can measure, because you will certainly know the radius of this circular arrangement. If this is the radius r, magnetic field you just applied, charge you know, the particle mass of the particle you already know, then you can measure the velocity of the particle. Now then you can measure the kinetic energy of the particle, the kinetic energy of beta particles. Now this is an important result, that the kinetic energy of beta particles comes out something like this: b square e square into r square upon 2m. Now if you move further, now why there is a need of neutrinos, why there is a need of neutrino hypothesis. So first of all, if we see that the number of beta particles graph with respect to the energy of beta particle, like in with respect to a particular beta particle, now there are many particles are coming out, beta particles are coming out continuously, because there are huge number of atoms inside a particular crystal arrangement. There are huge number of atom, and each nucleus is getting converted to another nucleus by transforming some masses or beta particles are coming out. That implies that there are many number of beta particles are coming out, but energy of each and every particle, every beta particle, is not a constant energy. The energy is changing with respect to each and every beta particle, and this is experimentally measured. So when they plotted the graph number of beta particles with respect to energy of beta particles, then there are every kind of distribution. The distribution is something coming out something like this. There is a continuous distribution, and with respect to this continuous curve, you can actually say that some number of beta particles having this energy. Okay, some have this energy, some has this energy. Okay, you can measure this, and then you see that why each and every beta particle does not have the same energy, where this energy is getting converted into. So actually Pauli initially explained this, and Pauli said that actually there are some another particles are coming out as well, and these particles also define the process such that there is a conservation of angular momentum also takes place. So he explained neutrinos and antineutrinos in the processes, that with respect to this process you will have a neutrino beta negative decay, you will have an antineutrino. For with respect to beta positive decay, you will have a neutrino. So he actually explained initially, and then there was the origination of this neutrino hypothesis. Because of this graph you can understand the need of this neutrino hypothesis. Okay, so because of this graph we have Wolfgang Pauli proposed that an additional particle with zero charge and negligible mass, was also emitted in beta decay, and the particle was named as neutrino. So this is our second chapter got completed here. You try to understand this and do some questions on this, some process to understand here are alpha decay and beta decay. Okay, so in the next classes we will be discussing about some nuclear reactions and the energetics of the nuclear reactions, and how we can accelerate the particles, like we will discuss cyclotron, betatron. Okay, thanks.